Hello everybody and welcome to my presentation titled by Side Channel Attack Resistance of the Elliptic Curve Point Multiplication using Gaussian integers. My name is Malek Safieh. So the most used public key crypto systems nowadays are the RSA and the elliptic curve crypto systems. The elliptic curve crypto systems are usually used for small embedded systems due to the small key length. The elliptic curve crypto systems are based on the elliptic curve point multiplication, which is the most expensive operation. Hence, coprocessors are considered that are optimized for the calculation of the point multiplication. These coprocessors are prone to the so-called side channel attacks. In this work, we show that the performance and efficiency of the side channel attack resistant point multiplication can be improved using Gaussian integers. In order to show this, we consider first the point multiplication. There exist several algorithms for calculating the point multiplication. We consider here the add and double algorithm. As we can see in this algorithm, the inputs are a key and a point on the corresponding curve. The output is the point scalar multiplication of both. So the calculation in this algorithm is based on 2 point operations, namely the point doubling, double, and the point addition, add, which are calculated using prime field arithmetic. The problem is that the add operation is calculated only if the current bit of the key is not equal to 0. Hence, the processing time and power consumption depend on the key. I was asked to give an overview of the possible attacks. Hence, we consider first the simple power analysis and timing attacks. Later on, we present the differential power analysis. This figure shows the concept for small embedded systems. As we see, in addition to the primary processor, we have a coprocessor for calculating the point multiplication. Now, depending on the current bit of the key, the point addition may be calculated in the actual point multiplication iteration or not. Hence, an attacker can estimate the current bit of the key by measuring the power consumption of the coprocessor over time. There exist several hardware attacks in the literature. As mentioned before, we have timing attacks, simple power analysis, and differential power analysis. But we focus first on the first two. We have here an example for the power consumption of the coprocessor over time. As we see, 2 double operations are calculated successively here. Hence, we know the current bit of the key is 0. Otherwise, it is 1. To avoid this, many implementations consider a dummy add operation if the current bit of the key is 0. This results in a constant calculating time and power consumption of the coprocessor. In this work, we consider the t-adic expansion of the key, which is calculated using this algorithm. The inputs of this algorithm is a key and a base tau, and the output is a simple base conversion of the key of length L, which is usually smaller than the length of the binary keys. In this work, we consider k, kappa, tau as Gaussian integers, which reduces the calculating complexity. Now, consider the modulo function here. Tau and kappa are Gaussian integers. Gaussian integers are a subset of complex numbers, such that the real and imaginary parts are integers. So, We have here two examples for tau is equal to 2 plus I and 16 plus I. The modulo function to calculate the kappa I in the previous algorithm results in a Gaussian integer, which is one of these points. Next, we consider the point multiplication with the new resulted expansion of the key. This was the point multiplication algorithm for binary keys, and this is the point multiplication algorithm with the t-adic expansion of the key. As we see, we have L expansions, which also define the number of iterations of the algorithm. The product tau r is a point multiplication. For instance, we need one double and one add operation to calculate this product for tau is equal to 2 plus I. Hence, each iteration requires more point operations. However, the number of iterations L is reduced and we have lower calculating time for Gaussian integers. But an attacker can detect all digits with kappa I equal to 0, where the point addition operation is skipped. In order to avoid this, we present a new expansion algorithm which excludes all 0 elements. This was the previously considered expansion algorithm, and this is the new proposed algorithm where the 0 elements are replaced with tau. This algorithm results in the same point multiplication where the derivation is in the paper. Consequently, the add operation is calculated in each iteration of the point multiplication, independent of the value kappa I. This prevents simple power analysis and timing attacks. However, the second summand of the point addition is a point multiplication that requires different number of double and add operation. On the other hand, the point P does not change during the whole point multiplication algorithm. Therefore, we pre-compute all possible products kappa IP and store them in a memory. Depending on the current kappa I value or digit, the corresponding product is read from the memory. This results in fixed number of add and double per point multiplication, independent of the value kappa I. Furthermore, Gaussian integers are symmetric. Using the sign magnitude format, we store only products for all possible kappa IP from the first quadrant, marked here with filled points. All products in the other quadrants can be achieved by negating the sign of real and imaginary parts. This reduces the calculation time for the pre-computations and requires fewer memory. Now we consider the results. We approximate the calculation complexity by the required number of multiplication equivalent operations. We consider a binary key with 163 bits and compare the results with the fixed base variant and the proposal from Hedabu, which aims on reducing the required memory. As shown in this table, using Gaussian integers, it reduces the number of multiplications and the number of stored points or the memory requirements. Now, conclusion. In this work, we illustrated that Gaussian integers can reduce the calculation complexity of a point multiplication. Using the new key expansion algorithm, we can secure the calculation of the point multiplication against simple power analysis and timing attacks Furthermore, we showed that Gaussian integers can reduce the memory requirements. So, outlook. Now, we consider the differential power analysis attack. Gaussian integers can be also used to prevent differential power analysis. As mentioned before, the coprocessor contains a memory that stores all possible products, a kappa IP. This type of attack is based on statistical analysis to find a correlation with the current value kappa IP, which is read from the RAM, from the memory in this case. Yeah. So using Gaussian integers can prevent such an attack, but the point multiplication have to be extended with the randomized initial point concept from Hedabou. This increases the memory requirements for Gaussian integers, but the calculation complexity is still reduced with compared with other integers. Thank you for your attention.